Hello friends, welcome back to the bench. Today we have a curious case of a Surface Pro 4 that came from another repair shop. It didn't come from another repair shop for repair. I bought it from another repair shop as they deemed it as not worth fixing, I assume. What happened to it? It's actually pretty curious because you see this is disassembled, not screwed in. There's the bracket missing over here that should be holding this. Not sure what happened here. It's kind of like maybe it was pulled, hard to say. This was deformed, this shield, and the only shield that was taken off. The screw over here is missing, so I assume the whole heatsink was removed along with the fan. The fan is connected, so it was reassembled. I assume what happened here, because this is not the original battery. So I assume the battery has been replaced, so the laptop came in for battery replacement, and it just stopped working after the replacement. That's what I would assume, because it's weird that this is not screwed in, and technically you could try to replace the battery without removing the board completely, just unscrewing these screws and just kind of lift the board. It's very difficult. I would not recommend that method, and you're risking damaging the board, and perhaps that's what happened here. My second thought was that since this shield is the only one removed, then someone just checked the resistance on VCC core, and GT1, GT2, it was low, so they figured it's most likely the CPU. But would the CPU get shorted because of battery replacement? It could be, but let's just check it out. So first let's check our resistances over here. So this is our VCC core, right? These two MOSFETs are driving this coil. We would have roughly about 800 to 800 millivolts to a volt, something like that, and that supplies the CPU. Oh yeah, CPU is over here, right? Let's get a smaller zoom actually. So we can see a little more. And this is GT1 and GT2, also supplying the CPU. So these three coils are responsible for supplying CPU. Now we start by measuring resistance, and we should see around 12 to 15 ohms, and we see 6.7. 6.6 on this side, and GT1 6.7 and GT2 6.7. So that points us to the CPU being faulty. But before we actually make that determination, let's check the voltage on the other side, if it's also low. This shield has not been removed, so that's good. And one of our most crucial voltages will be generated by this coil. And let's check the resistance to ground. And we have 6970. So if the CPU was shorted, I would expect lower here. This should be around 100, so we are a little low on this one. But that actually is not too bad. So let's do this. Let's check our EC, VCC EC. That is the voltage crucial for this device to start, because For this device to start, we need a signal from VCC. This is actually shielded here, so we're not gonna see it. But underneath this shield, we have 2 transistors that supply voltage, 15 volts from the charger. Now, for that to open, for those transistors to open, ECC needs to get power good signal. So our 3P3 VCC needs to be present. Then it will emit, then it will open those first 2 transistors. Once it does, we have the voltage. Oh, this is different size. What was that voltage called on the? Let me flip the board up. On. Well, looks like here it's called XPWR or BAT, so external power or battery. And indeed, this will also be the battery voltage, but that also creates a VCC. What was it called? I think it was called system VCC, system VSys. Yes, it was called VSys. So VSys is also referred to V always on or V always present. Without that voltage rail, we can't really do anything because nothing gets powered up. Oh, did I get the right one? No, of course not. I disconnected power button instead of fan. Come on. There. And we are interested in this shield over here. So our EC chip is here underneath this shield, but our first VCC, oh, I messed that up. Come on. Our first voltage comes from the linear regulator, and that translates into VCC. It translates into 3P3 VCC that later becomes 3P3 VCC EC, which supplies EC chip. Without power supply on the EC chip, nothing's gonna start because it's the EC chip that decides whether the machine starts booting or not. Actually, not even booting, whether the power converters turn on or not. This shield is gone. I don't know. I think it was removed and then just put on improperly. That's why I couldn't get it off. Maybe, or maybe I just suck. This one has been removed, so I think the board has been removed. But there's no way to remove the board without removing this plastic thingy here. Or at least I was never successful. But maybe if you remove these, well, whatever. Okay, and what we're interested in here are these 2 resistors here. Am I still, yeah. This one and this one. On here we have a 3P3 VCC, it's delivered by this coil. Is it? No, that's the linear. Yeah, it's... no, forget that. This is the linear regulator. So if we have a short here, let's see, on EC, and we have 1.1. Oh, 0.9, 0.8, yeah. So we have a short on VCC EC. So that might not be the CPU short. It could be something else. And since I suspect that this... oh, but this is ground, is it? Yeah, so we have 0 on 1.4 here. 0 here. I guess this is ground. Let's see on the board view, just to make sure. Let's flip the board here. It's in front of the CPU. There's the coil. Yes. Yes, so this side is voltage, this side is ground. Yes. Okay, over here, yeah. Now let's see if V always on, which one was it? This one? Yeah. On this cap, this is V always on. So if there's no short here, yeah, this is good. So our always on is okay, so that's what supplies this, and it produces 3.3 V, 3 VCC, which for this resistor supplies VCC EC chip. So if we have a short here, let's just inject some voltage. We had pretty much dead short, almost a dead short. So we don't need high voltage. We probably can do it with 800 millivolts. Not even. But let's first drop it down to 1 volt. 0.8. And our current, maximum current, will set to 1 amp. And OCP enabled. So the power supply will turn off if it exceeds 1 amp. Just in case. And let's inject in here. There's a lot of reflections, so that's gonna make it harder, but let's see. 700 milliamps. Okay, nothing's getting hot, so let's get the shields off. Oh, okay. Here we are. It's the EC chip. Yeah, see that? Oh, I don't know if you can see that. Let's see. See? Boom. One here. Yep. That is the EC chip. Let's confirm. Yeah. Beautiful heat spot. 38 degrees, 39. Yeah. So our EC chip is fried, so it's not CPU. So whoever deemed this to be an unrepairable due to shorted CPU was wrong. It's not CPU, it's EC. So how can you easily get fooled? When you measure resistance here and it's low, then you naturally inject voltage here or here and see what's getting hot. First thing that's gonna get hot is gonna be CPU, but that's normal. Hang on, I'm not showing you. Okay, you inject voltage here or here, right? Basically on this coil. You could also inject on these. And the first thing that's gonna get hot is the CPU, and this is absolutely normal. That's what CPUs do, and that's why they have heat sinks, right? So you have to ignore that, because one of the memory chips could be faulty and shorted, and that will also cause this CPU to light up on the thermal camera. That's why I never go to injection over here until I confirm that my VCC for EC rail is okay. Because if it's not, then even if the CPU isn't shorted, it's still not gonna work. And in this case, our EC is shorted, which is too bad, because I'm not sure if I replace ECC or EC, will it work? I'm not sure, because it should be paired with something. And usually on laptops, when you replace, oh no, maybe that was PCH? No, EC. Yeah, if you replace the EC chip, you have to clean the BIOS. But I do BIOSes on these, and I never have any issues with that. So I'm thinking perhaps if we do replace the EC chip, this might work. So this is the BIOS chip, this is the C, and this is, I don't know. I never had to do anything with this one. So let's just do this. What do we have set? 390, that's a bit too much. 385, 100. Let's remove the EC chip and see if the short is gone. That will be step number 1. Now let's see how board is cooling down. It's surprisingly, it doesn't seem like a thick board, but it soaks a lot of heat. Like even to desolder the BIOS chip, you're not gonna do it at 375 at 75 airflow. For some reason, it requires at least 390 at like 100 at least. I went up to, how far did I go? To 115. 398 to 115. Okay, is it cool enough? Because we don't want to measure when the board is really hot and because the properties of semiconductors change when they get really hot. Also, we don't want to have a short on this guy over here, on this wire, so make sure it doesn't make the connection. And let's see if our short is gone. The short is not gone. We're still getting pretty low over here. So was the EC chip just a coincidence? Or there's something else going on here? Only one way to find out. The board is still pretty warm, so it's gonna be hard to see what's heating up. But let's give it a try. Yeah, the board is at 41 degrees. Needs to be cooler, because that's roughly what the component is gonna heat up to. But let's see. Oh, but yeah, okay, something else is wrong now, because now we're grabbing more than an amp. So I made a short somewhere, possibly by removing the chip. Is it because it's warm, or this wire here made a short? But no. Oh. Why are we taking more now? Let's try with 1.5 amp. See how much is it gonna grab. At 0.8, I'm not worried about frying anything. Yeah, over 1.5. That's weird. So this is like dead short now. This sounds more like like there's actual short, like a bridge. Did I make a bridge on ECC? Let's see. It's possible that there's a short on ECC. Not ECC, the EC chip. I keep mislabeling it. Okay, this will ensure that there is no bridge under EC. There's a fair amount of flux, but that's fine. And let's see again. Was it the bridge? Well, we get 3.8 now. 3.5. Still a bit low. How much should it be? Let's check on the reference board. I'm pretty sure it should be kilo ohms. Yeah, 26K, 30, 4, 15, 8. Well, the cap is charging, that's why. 4K, yeah, that's right. Now I remember. It should be 4K. And we're getting low, so. But now at least the board is not gonna soak. So there must have been a bridge here. So that's why it was dead short. Now it's no longer dead short, but something else is also shorted. the EC chip was shorted, but something else is as well. So let's see again. Oh my god. Oh, you're so weird. Okay, now it's at 30 degrees now. Let's see. Yeah, now we're grabbing 65, 23 at the moment, 23 millivolts. It's 23, what am I saying, millivolts? Milliamps. And we're injecting 0.8 volt. So since it's not a dead short or not low resistance load like it was before, this will not show up on the camera, especially since the board is pretty warm. So in this case, normally what I do is I just put the board in the fridge, or if it's winter time, I just put it outside for a while, meaning like 5-10 minutes, let it cool down, and then with low voltage you can detect the short pretty quickly. When the board is hot, it's a lot more difficult. But now we're grabbing pretty much nothing. 0.004 amp. So definitely our EC chip was at fault. Oh, now we get 79 okay, so the board was hot. That's why I was getting crappy measurements. It still should be lower, but the EC chip is gone now. So our measurement could be different. Now let's see on the... We still have low on the CPU. And on GT as well. And actually lower now, probably because the board is hot. Before it was closer to 6, now it's closer to 5, below 5. But that didn't do anything for us. Well, it didn't do anything. We know the EC chip was at fault. But even if I replace the EC right now, we still have low resistance here. But our low resistance doesn't grab much current. So let's go to 1.6 volts and see if we can spot anything. But at this time, I think the CPU will be getting warm. Hit it. Oh, it is hitting. Okay, oh, but we're grabbing 14 milliamps. So that's not gonna show up as anything. So let's just keep raising the voltage until we're satisfied with current. But at 3 volts, we're grabbing only 47 milliamps. That's not enough to see under thermal camera. At least not my thermal camera. Now, this is our limit, because if I inject more than 3 volts, 3 volts is already too high. But if I inject more than 3 volts, probably more than 3.5, something will blow, because this rail is 3.3. So now let's just see, maybe let's just inject the CPU and see. Well, that's not gonna tell us much. CPU is gonna get warm, and we know it's gonna get warm because the resistance is too low. But not 3 volts, 1 volt. That should be plenty. And let's grab this and let's inject like this. Yep, the CPU is warming up and we're grabbing half an amp. But only the CPU is getting warm, nothing else. As I said, mind that CPU will get warm either way, so it's kind of tough to spot it if you have both CPU and your shorted element inside. So try to maneuver the camera in a way so you only see around the CPU, not the CPU. Okay. Alright, so the conclusion. Well, the other repair shop appears to have been right. The CPU is fried. But that doesn't mean they did everything right, because EC was shorted as well. So in this case, well, at the end of the day they were right, but they could just as well have been wrong. And this would have been an easy fix for me to just replace the EC. Because I cannot replace CPU, and that's not because it's pairing or anything like that. I don't have proper tools to remove the CPU, not to mention solder it back on. Actually, even with the EC, when you get it from the legitimate source, EC comes pre-bowled. So all you have to do is just put some flux, put the chip on, heat it up, make sure it's sitting right, and you're done, and the computer is working again. If, on the other hand, you want to replace it from a donor board, well, that's a bit more tricky. There are some ways to do it without the stencil. I mean, you can use the balls individually, and I've done that before, and it is a pain. It's very time consuming, and it's definitely not worth it. No matter how much you charge for it, it's just not worth it. It's too frustrating. The other way is to resolder, to just put the solder on the board over here, enough on the board and on the chip, enough that hopefully the chip will sit. But then you kind of need to gently press it after soldering, which normally you don't do when you rebowl. You just kind of tap it from the side to make sure it's floating nicely and it falls into position, and that's it. You don't press on them. But in this case, if you just put some solder on the board and some solder on the chip, you have to gently press it. But I mean really gently. And it sometimes works. It's kind of like 50-50, because there's no way to ensure that you'll put the same amount of solder on each connection, and there's no way to ensure that none of the pins is going to be starved from solder. So if you pull that off, that is possible. But as I said, it's kind of 50-50. So I wouldn't recommend this method. Now, to replace this one, you need a stencil or pre-bowled chip. But that was pretty much it. The conclusion of it is, even if you have low resistance on VCC core, always check the EC rail. in this case, it didn't really have anything to do with it. And actually, you know, this computer, after EC replacement, this computer might actually turn on. Let's check the resistance again on vCore. Yeah, 5.8. It's still pretty low, but it should be 12, right? So it's 50% off. It's not that short. Shorted CPUs can work in limited capacity. Obviously, it's the performance of such computer would be awful, and you need really good cooling for it to work. I've never tested that on these machines because in general these machines do not have the best cooling. That's why those CPUs tend to short out. But on the bigger computers, it is possible when the CPU is overheating, just put extra cooling on it, and it will perform, because there's a lot of redundancy in those CPUs. So partially shorted CPU doesn't mean completely not working CPU. It means partially working CPU. Not something that you should use, obviously, but technically, I don't know. I've used one computer that had partially shorted CPU, and I've used it for a long time. And it was a laptop, and I had the additional fan installed at the bottom, connected to USB, and it would just additionally blow the air, and the computer worked for me perfectly. It wouldn't freeze, it wouldn't anything, it wouldn't, you know, it wouldn't crash. It was very inefficient. It was definitely not a gaming machine anymore. But you could freely, you know, watch movies and, you know, browse the internet. It would just severely overheat, and I'm talking like, you know, it would stay at around 80 degrees, 70, 75, 80 degrees externally. That's not the core temperature, externally, because I had the sensor on the heatsink. So heatsink would get to those temperatures. So the temperature of the core was much higher. I didn't check, but yeah. So yeah, this could work after replacement of EC. But this is pretty much the bottom line. And in the next video, we're gonna attempt a data recovery, because in this one, the SSD has been removed. There you go. Professional removal. SSD was removed because I assume after the battery replacement, the computer wouldn't work. So they just took out the SSD, the only thing that you can actually take out of it, because to remove the battery takes a while. Oh, yeah, it was definite. Well, we know it was removed because this is not original battery, but this isn't even glued. Well, I guess it's glued on this side. On this side, yeah, it is still pretty sticky, but you should put adhesive on this side and then put it on to keep the battery, because otherwise this can happen, and that's not good, because that's going to be pushing on your screen, and that's going to break your digitizer. So yeah, definitely make sure the battery is glued in correctly. And that's pretty much it. I hope you found this interesting. These machines are very nice and very easy, or at least in my view, they're very easy to fix, because I have all the schematics and board views and everything, and I have plenty of these for reference, right? So I always keep one of these over here with all the shields taken off, battery is off, and I just take the measurements. And just in case you are curious if I wasn't lying about the vCore resistance on a working machine, the vCore resistance is 13, because it's cold. It'll get down when it warms up, it'll go down to roughly 12. but that should be our resistance. And on G1, GT1, 13, GT2, 12. So these are the normal resistances that you would get. And on our rail, that goes also to CPU. Yeah, that should be around 100. And on our other one, it's around 50. So definitely CPU is at fault on this one. Alrighty, fellas. Thank you very much for watching. And I shall see you